Hi, my name is Andrea Girones, and this presentation is going to be about the equipment I'm using for solar observing, some of the features on the sun that we can observe from Earth, as well as some of the interesting activity that's been going on the sun over the last few months. I am recording this because last time I was supposed to give this presentation, I came down with laryngitis. So better safe than sorry. I have recorded this and I don't think you'll be seeing my face for the rest of the presentation. Many of you know I began my solar imaging with a small and portable LUNT 40 telescope. I think it gives me great images and it's certainly a reasonably priced way to begin taking H-alpha imaging. This is an example of one of the images that I took with the LUNT 40 millimeter H-alpha scope. I normally image in monochrome and then I add false color in Photoshop, and it is clearly a very capable imaging solar scope. Solar activity is increasing in 2023 and there are more and more storms, sunspots, and solar flares. I rely on these three sources of information. The Space Weather Live, there's an app and a website, as well as the Gong website, which provides live H-alpha views. It's really good to go and see what's happening on the sun. And space weather woman Dr. Tamitha Skov is a solar physicist, and she has a YouTube channel where she is updating you on the current CMEs, solar flares, etc. I do a set of solar images. I usually on my phone, I take a snapshot of the Space Weather Live sunspot region map. And then I also take a snapshot of the H-alpha images from the Gong network. So the Gong network has H-alpha telescopes set up across the world. And so you can always get like an up to the minute look at what's happening on the sun. And you can look and see if there's anything interesting, if there's a big filament. And it's a great way of not only finding out what's happening on the sun, but sort of keeping track of things. I like to merge the two bits of information because as you can see, the sun is just so active right now, it's hard to keep track of all the active regions. The third source of information that I mentioned was Dr. Tamitha Skov's YouTube channel. She does a lot of, she does a weekly update on solar activity, and she has a lot of mini courses on the sun and space weather on her website. It's fabulous. I highly recommend it. New solar equipment update that I did to try to get a deeper, high resolution, more detailed images of the sun. I now use a quark chromosphere solar filter, and I have a Starfield Optics 102 millimeter refractor, and I use those two pieces of equipment with the ASI 174mm. It's a monochrome planetary camera. Pictures of my refractor and some of the things I use for solar imaging. Obviously, with the H-alpha setup, I have a quark. It is sitting in a diagonal, and a lot of people use a diagonal both for imaging and for visual use. You can over on the other image, you'll see that I have stopped using the quark so that I can do a white light image. And also I have at the front of the telescope, and I'm going to point it out here, this is a homemade white light filter. I purchased a Bader solar paper and I made a cardboard holder and I use that for solar imaging. I am still using the same camera and the diagonal, but there is no quark for white light. This is my quark imaging train. I ended up going for a straight through train. I wasn't crazy about the diagonal. At the front, I have a UV IR cut filter. This is an energy rejection filter. If you are using a telescope greater than 102 millimeters, you actually need an external ERF. This part here is the actual quark in the middle. It has a tuning knob and there's a little plug here where you actually need to give it power. Here I'm using a reducer. Because the quark has a built-in Barlow. It's actually a very, very narrow field of view on the sun. Many people use a reducer to then widen the field. And that is very helpful to get if you're going to try to do a full disk mosaic. You'll notice here that I'm actually at this point using an ADC, atmospheric dispersion corrector. ADCs are typically used in planetary work, so I happen to have one for my planetary work. What I'm using in this situation, I'm using it as a tilt adapter. Anytime you do solar imaging with Barlows, you run the risk of having Newton's rings. These are these funny rings, they're called interference rings that show up in your images, and they're really hard to get rid of unless you have a mechanism to tilt the sensor. And I can use an ADC, and you can use a tilt adapter. I think Tony uses a tilt adapter. Things about solar imaging is you can buy an inexpensive white light filter and really see a lot of interesting detail in white light, such as sunspots, granulation, faculae, which is white areas like plages along the edge. With white light, you are looking at more of the surface of the sun, or it's called the photosphere. And right now, because it's so close to solar maximum, white light imagery is very fun. A couple of images of my imaging train as it is now, straight through and all threaded. The reason I have it all threaded is because I didn't want to have any movement, because I take flats as well for solar imaging, and any movement in the imaging train can affect the flats. They won't work anymore. Quarks, by their nature, have a little bit of an uneven field, so using a flat frame is very important. There are different ways to take flats, and if you ever need questions about flats, I can answer those. What I have here is I'm going to get the little pointer. I've actually also done a double stack where I managed to mount the Etalon for my Lunt 40, and that's given me a double stack. So now I have a variety of configurations that I can use. I have with the reducer, without the reducer, and I have a double stack. And I'll just run through a couple of images so you can see the differences. An image of a sunspot from, gosh, I think this is near the end of June 22nd, and I've forgotten the name of it. This is what it looks like with a reducer. And it is a pretty nice and wide field of view. And I quite like the sampling at this magnification as well. You can see in this image, you can clearly see the dark umbra, you can see the lighter penumbra, and you can also see some of the fibrils, which are the dark lines going along the magnetic field. Now just keep an eye on that little sunspot because I'm going to show you what it looks like with the reducer. Without the reducer, and the field of view gets much smaller. What it looks like without the reducer. So as you can see, just using a quark without a reducer, you have a big, very deep field of view, very deep look, very narrow field of view. It's very nice, it's very detailed, it's very high res, but you don't get the full disk unless you have a much shorter telescope, and it's a lot harder to do a mosaic without getting lost in the sun. But I like the detail. I love being able to zoom in like this. Now this image was taken with the double stack and it's no reducer as well. I haven't quite finalized my technique with the double stack, but I do think that it gives a slightly different look. We are looking at a different layer of the chromosphere. We are seeing less of the penumbra, and we're seeing more of the spicules, which are the little hedges, and more of the fibrils, which are higher up in the chromosphere. A lot of people do double stacking with solar imaging because you are trying to narrow your bandwidth and get greater contrast. But I'm quite enjoying the double stack, and I think it shows a lot of promise. One of the ways to learn a lot about the sun was to complete something like the Astronomical League's H-alpha certificate. You need to document either by imaging or with sketching a variety of different features on the sun. different kinds of prominences, different kinds of features, and you also need to do a full disk, uh, 30, 30 of them, so that you can map the sun through 1 or 2 rotations. Example of a filament, it is the dark S-shaped. Filaments are basically solar storms that are on the surface of the sun. And there are tons of filaments, and they are very important to space weather, as we will discuss a little further on in this presentation. But this is one of the features you have to document for the certificate. Feature that you have to document for the H-alpha certificate are prominences, and not just any prominences. They want you to document a whole range of features. Some of them are pyramids, some of them are arches and loops, hedgerows. You get to learn all the different terminology. A prominence as well is basically a filament seen on the edge of the sun. So as a filament gets close to the edge, it goes from being a dark filament on the surface to being light against the darkness of space. And when you have a filament that goes over to the edge and then turns into a prominence, it becomes a philoprom. That you need to identify are spicules, and they present as a chromospheric fringe. And you can see along the edge of the sun, there's a little fringe there. They are tiny, short-lived little filaments rising up and down and are about the size of the Earth. On the disk in H-alpha, spicules appear as dark hedges or little bushels of spicules. A couple of features here are plages. Plages are named after the beaches in French word for beaches. And they appear like a beach because it's a beautiful white area that surrounds the dark sunspots. And plages are always usually related to sunspots. And fibrils are the dark, elongated structures. I'm going to take the pointer here. These are the dark, elongated structures, or chromospheric structures that align themselves along the magnetic field between the poles of a sunspot. That you're required to identify is something called an emerging flux region. And that is sort of exactly what it says it is. It is an area that is turning into a sunspot region. And what you're seeing are a bunch of flux tubes rising up through the chromosphere, being pushed up through convection. And eventually, over the next couple of days, this area will become 2 sunspots and an active region. Later on, I have a little video time lapse that I took of a filament, but it also has 2 emerging flux areas in there, and these areas later became sunspots. Another feature that you have to identify is something called an Ellerman bomb. Now, it's kind of unclear what an Ellerman bomb is, and they're very hard to locate information on. So if there's anybody out there who knows what an Ellerman bomb is and can explain it to me, I would love to hear from you. But it is described as tiny little micro flares surrounding sunspots in an active region. So you'll see near these sunspots, there are these little bright little tiny spots. You really kind of need almost a time lapse to see them sparkle. But that is what I believe are Ellerman bombs, although I'm open to being corrected. I'm going to switch to some of the activity that took place during May, June, and July, and just sort of like what's new on the sun. This image, actually, just by way of example, is one that I took with my double stack setup, and it is inverted so that those dark filaments actually appear white on the surface of the sun. In May, we had what is called a reverse polarity sunspot. Usually all of the sunspots, say in the northern hemisphere, follow the same pattern. A positive spot leads a negative spot. And in reverse, the reverse occurs in the southern hemisphere. In May, we had active region and sunspot 3296, which had a reverse polarity appear. This unstable magnetic situation right next to another sunspot AR 3293, caused multiple solar flares to be launched and sparked all of the whole time it traveled across the face of the sun. A bit of information you can get from Space Weather Live, and for all of the sunspot regions, they show the magnetic makeup. And you can see here that region 3296 had red leading and blue following, which is the opposite of what is supposed to happen when you are in the northern hemisphere of the sun, at least in this solar cycle. After the next solar cycle, this is likely reversed. Most interesting things that happened on the sun over the last couple of months had to do with filament launches. And you'll recall that filaments are these large features on the chromosphere of the sun, and that if they launch, basically it's sending a huge amount of material in a coronal mass ejection towards Earth. Sometimes it comes towards Earth, sometimes it doesn't, but when it comes towards Earth, it can have a lot of implications for space weather and the Earth geomagnetic activity. This is imagery from a program called a J Helioviewer. It is from SDO and 304 angstroms. Now, the reason I'm showing this to you is that on June 12th, there was quite a dramatic and beautiful filament eruption from the polar filament. And if you watch at the very top, you will see it launch. I'm going to see if I can do it again. It's up in here. And there it goes again. Whoosh! And some other activity occurs down on the Earth strike zone in the western side of the sun. Same imagery, but shown, whoosh, there it goes, by a coronagraph. And essentially, this gives us a better idea of whether or not a filament launch is actually launching material towards Earth, whether it's heading off in a different direction. And as you can see, that wasn't the only CME launch that day. The number of CMEs being launched every day is increasing steadily, and it's making many people feel we are much closer to solar maximum than we thought. We thought this filament may be Earth directed, but we did not, in fact, have a geomagnetic storm. But it was a beautiful launch. On June 20th, we had an X-class flare from active region 3341, which was coming around the southeast side of the sun. This was, I believe, one of 2 or 3 X-class flares in June. We haven't had very many so far, and none of them have been in the Earth strike zone. Which is lucky because an X-class flare can be destructive, but so far nothing has been pointed towards us. Is again, the imagery for that day, and I think you just saw, heading off to the east side of the sun, you can see what the X-class flare launched, and it was not insignificant. So as much as we are excited by X-class flares because they show increasing activity on the sun, if they are aimed at Earth, they could be quite dangerous. But you can see from this little imagery that lots and lots of material is being erupted from the sun every day. So this is a little time lapse that I took the next day, June 21st. This presentation was supposed to follow Tony's, and you recall that in Tony's presentation, he looked at this straight up and down prominence and wondered what on earth it was. I imaged this area the next day. It was in the northeast, just rotating into view. And you can see in this little time lapse that the little tiny prominence is linked with the larger, thicker prominence. Another feature of the last couple of months has been the appearance of ginormous sunspot regions. This was active region 3354, and it was just a monstrous looking grouping on the face of the sun. It was often compared in size to the drawing that was done about the Carrington event. That was a big solar storm that impacted Earth. It's impressive in H alpha, but it's even more impressive in white light. And I did take some imagery of that the next day. You can see in white light, there wasn't much happening on the sun other than this one massive area, and it is huge. I could not get a stacked image because there was too much cloud, so I just took a picture of this, posted the video, which shows just how big the sunspot area was. There have been other areas even bigger since that day, but the fact that we are getting more and more massive sunspot regions, again, is pointing towards solar maximum. That's the white light image I took the next day. As you can see, it had practically rotated out of view, and it was still pretty big. I have decided to update this presentation with a few things that have occurred since the last presentation, and namely a bunch of filaments that were launched near the end of the month. This filament, you can see there's a big S in the middle. You will notice that it will pop out, and there is also quite a dramatic and beautiful CME along the northwest edge, which you will see better once we get to the coronagraph. So I'm not sure if you can see it. It was right in the middle. We'll go to the next slide and see. This, once again, keep an eye out to the northwest limb. There'll be a big, beautiful ejection that way, and there were quite a few CMEs launched on that day as well. It's unclear. None of them really caused aurora, but there was some hope that they might, because as you can see, whoa, there were quite a few that went off that day. The white speckles that you see on the coronagraph are a result of radiation storm that was also launched. Since there had been so many filament launches in the past few months, on July 30th, I took this time lapse of a large filament on the sun. Sadly, there were no filament launches on that day, but you can see around the sunspots there are some dark, sort of gurgling and bubbly areas. These are, in fact, emerging flux regions, and later on they became AR 3392 and 3393. Okay, and this is my last filament image. I just want to do a quick update because on July 31st, August 1st, and August 2nd, you can see 3 storms were launched. It's sort of hard to see on this imagery, but you can, if you look towards the west side of the sun, you can see some material launching, and were a lot of flares. These 3 storms came to Earth all within 12 hours and greatly disturbed the geomagnetic field, and that resulted in a geomagnetic storm the night of August 4th. Thanks to the space weather forecast from Dr. Tamitha Scott, I knew that the solar storms were going to hit the evening of August 4th, and I was able to be there and take this time lapse as the aurora developed. That is the end of my presentation. Thank you very much. If you have any questions about solar imaging or space weather forecasting, I'm happy to answer them. You have my email here. You can send me an email anytime.